Have you ever wondered how your computer can handle, I don't know, a dozen open tabs, a 4K video playing, and a huge spreadsheet all at the same time without just melting? Well, the secret isn't some single magic chip. It's actually a brilliant, multi-layered system, a real pyramid of power. Let's dive in. So right off the bat, why a pyramid? It seems kind of random, right? But it's not. It is an incredibly clever design, and it is the absolute key to making our computers feel so snappy and responsive. It all comes down to solving one fundamental and, frankly, massive problem.
And here is that problem. Your CPU, the brain of your computer, is unbelievably fast. I mean, it's a world-class sprinter. It wants data, and it wants it yesterday. But the place where we keep all that data, our hard drives or SSDs, well, by comparison, they're marathon runners. They have stamina, but they're slow. If that sprinter CPU had to wait for the marathon runner storage every single time, your computer would feel like it was stuck in quicksand.
So to bridge this massive speed gap, engineers came up with a truly elegant solution. Not just one type of memory, but a whole hierarchy of them, all stacked in a very specific order. Let's start by looking at this whole structure, the memory pyramid.
And this diagram, it shows the whole idea perfectly. Right at the very top, you've got the fastest, the smallest, and the most expensive memory. We're talking CPU registers. But as you move down the pyramid, each level gets way bigger and a whole lot cheaper. But it also gets slower. The whole system is built on this beautiful series of trade-offs.
And these trade-offs, they follow a really clear set of rules. As you go down from that peak, the cost for every little bit of storage just plummets. That's why we can have terabytes of storage without taking out a second mortgage. The capacity gets huge, but the access time, how long it takes to grab a piece of data, goes up. And because of that slowness, the whole system is designed so the CPU has to talk to those slow lower levels as little as possible.
Okay, so let's zoom in on that first big layer just below the peak, main memory. The best way to think about this is as the computer's immediate workbench.
Main memory is where all the action is happening right now. It's the temporary holding zone for every app you have open and all the data you're actively working with. And it's made up of two main characters, RAM and ROM. All right, now RAM, or random access memory, comes in two main flavors. Now this table lays them out, but there's actually a little flip-flop in the info here we need to correct. It's SRAM, the static RAM, that uses the really fast flip-flops, which is what makes it perfect for that super fast cache memory we saw at the top of the pyramid. DRAM, on the other hand, uses tiny capacitors. They're simpler, which lets you pack a ton of them together, making it much cheaper and denser. That's why it's used for your main workbench RAM. It's just a perfect example of picking the right tool for the right job on the pyramid.
So the other piece of the puzzle is ROM, or read-only memory. Now, this isn't your workbench. It's more like the emergency instruction manual that's been bolted to the wall. It holds permanent, unchangeable code, and most importantly, something called the bootstrap loader. That's the tiny, crucial program that tells your computer how to wake up and get started the second you hit that power button.
Okay, so we've got a super fast CPU and a, relatively slower main memory. How do we bridge that gap? Well, this brings us to the first real piece of magic in the whole system, caching. Caching works because of this really predictable quirk in how programs behave. It's called the principle of locality. And all it really means is that when a program asks for a piece of data, there's a super high chance it's going to ask for that exact same piece of data again very soon, or maybe for the piece of data stored right next to it. And computers are designed to exploit this predictable little habit. So, to take advantage of this, engineers put a small, incredibly fast chunk of memory, the cache, right between the CPU and the main memory. It basically acts as a high-speed buffer. So instead of the CPU making that long trip to the main memory workbench every time, it first checks this tiny, super organized desk right next to it. And this setup leads to one of two things happening. When the CPU checks the cache and finds exactly what it's looking for, that's called a hit. It's instant, it's amazing, it's fast. But if the data isn't there, that's a miss, and that forces the CPU to make that longer, slower trip to main memory. The name of the game for the entire system is to get as many hits as possible and avoid those misses. So what actually happens when you get a miss? Well, the process is pretty straightforward, but it's also really clever. The CPU looks in the cache, comes up empty. That's our miss. So it sends a request to the main memory. But here's the smart part. It doesn't just grab the one little piece of data it needed. It grabs a whole block of data surrounding it and brings that into the cache, basically betting that the principle of locality is right, and it's going to need that nearby data very soon. But okay, how does the system decide where to put that new block of data inside the much, much smaller cache? One of the simplest ways is a method called direct mapping. You can think of it like a really strict library. A book from a certain section of the main library can only go on one specific shelf in the new arrivals cart. It's a really simple, really fast way to keep everything organized, even if it's not the most flexible system out there.
All right, that was magic trick number 1. Now, for the second one. What happens if the programs you're running are so big they don't even fit in your main memory to begin with? This is where the computer becomes an absolute master illusionist, using something called virtual memory.
Virtual memory is this incredible technique that makes your computer's limited physical RAM look absolutely enormous. It lets you run huge, complex programs as if you had an almost infinite amount of memory. It completely frees the programmer from having to worry about the physical limits of the machine they're on.
So how does it pull off this trick? Well, like this diagram shows, it uses your big, slow storage, your SSD or hard drive, as a kind of giant waiting room. The whole program lives there, but only the parts that are actively needed are brought into the actual main memory to be worked on at any given moment. And to manage all of this, the system breaks the program into these perfectly equal-sized chunks. Out there in the massive virtual space of your storage drive, they're called pages. And in the limited physical space of your RAM, they're called blocks. Your operating system is just constantly, cleverly swapping the pages you need right now into the available blocks. And just like we had a cache miss, if the CPU needs a page that isn't currently sitting in RAM, an event called a page fault happens. This is a signal to the operating system to pause everything, go find that required page on the disk, and pull it into an open block in RAM, which sometimes means kicking another, less used page out to make some room. So when you put it all together, you have the cache managing this constant high-speed flow to the CPU, and then you have virtual memory managing the much larger, slower flow from the disk to the workbench. What you end up with is this incredible masterpiece of engineering, built entirely on managing trade-offs.
Let's just look at that pyramid one last time. The cache acts as a speed boost for the main memory. And main memory, using that virtual memory trick, acts as a cache for the huge but slow hard disk. Each layer works to protect the layer above it from the slowness of the layer below it. And all of that, together, creates the seamless, instant feeling we expect from our computers. Ultimately, this whole thing isn't about one perfect kind of memory. It's about a whole team of specialists, all working together in perfect harmony. You've got the lightning-fast registers, the nimble cache, the workhorse RAM, and the vast archive of the SSD. Each one plays its part perfectly.
And all this leaves us with a really fascinating question. As our data needs just explode with things like AI and virtual worlds, are we going to need a whole new layer in this pyramid? What do you think the next great innovation in memory organization is even going to look like? Thanks for joining me on this one.